Hi students, in today's class we will study the analysis of double line to ground fault on an alternator. The power system faults can be classified into symmetrical faults and asymmetrical faults. The three-phase to ground fault is a type of symmetrical fault. In the asymmetrical faults, we study the single line to ground fault, line to line fault and a double line to ground fault. In today's class, we will study the analysis of double line to ground fault on an alternator. In this double line to ground fault analysis, we use the sequence networks and the symmetrical component transformation. Let me draw the equivalent circuit of an alternator. In the equivalent circuit, we have a voltage source in series with an impedance. This is our A phase, this is the B phase, this is our C phase. This is the neutral grounding impedance ZL. The phase voltages are EA, this is EB, this is EC. The three phase impedances are equal. It can be marked as Z. The three line currents are IA, IB and IC. This is an unloaded alternator. So the current in the three lines will be equal to 0. Now this is a balanced system because in all the three lines the current is equal, the voltages are also equal in magnitude and are separated by 120 degrees. So this is a balanced power system. So if you look at the sequence networks, you will get only positive sequence network for a balanced system. There is no negative sequence, there is no zero sequence network. Now we assume that there is a double line to ground fault on this alternator. So these two lines are shorted to ground. So this current is IB plus IC. The potential at this point is VB. The potential at this point is VC. This is equal to 0 as it is grounded. Now, when you consider this unbalanced power system, you will get positive sequence network, negative sequence network and zero sequence network. Because for an unbalanced system, along with the positive sequence network, the other sequence networks like negative and zero sequence network will also be added into the system at the point where the system is unbalanced. Now you need to find out how the three sequence networks are interconnected, whether they are connected in series or in parallel. For that you need to find out the sequence currents and the sequence voltages. Here in the first line, the current is still equal to 0. This phase current can be written as the sum of the sequence currents IA0 plus IA1 plus IA2. This is equal to 0. Now, we consider the voltages VB and VC. Both are equal to 0. So, VB equals VC equals 0. Now, let us find out the sequence voltages. VA0, VA1 and VA2. These are the three sequence voltages, zero sequence voltage, positive sequence voltage and negative sequence voltage. This is equal to 1 by 3 into a transformation matrix 1, 1, 1, 1 alpha, alpha square, 1 alpha square, alpha. into the phase voltages VA, VB and VC. VB equals 0 and VC is also equal to 0 because these two lines are shorted to ground. So from this matrix equation, the zero sequence voltage VA0 equals 1 by 3 into 1 into VA plus 1 into 0 plus 1 into 0. So it is 1 by 3 VA. Similarly, VA1 equals 1 by 3 into VA and VA2 is also equal to 1 by 3 into VA. So the three sequence voltages are equal. Let me write the voltages here. VA0 equals, VA1 equals, VA2. Now the three sequence currents, the sum of the currents equals 0 and the three sequence voltages are equal. So the three sequence network should be connected in parallel. Let us draw the sequence networks of an alternator here. This is the positive sequence network of an alternator. In the positive sequence network, we have a voltage source in series with positive sequence impedance. This current is IA1, the positive sequence current. Here the voltage equals, the positive sequence voltage equals EA minus the drop in this impedance. It is IA1 into Z1. Now let us draw the negative sequence impedance. This is the negative sequence network of an alternator. We have only the negative sequence impedance. There is no voltage source in the negative sequence network. The current is IA2. Here VA2 equals minus IA2 into Z2. This is the positive sequence voltage. This is the negative sequence voltage. Let us draw the zero sequence network of an alternator. When you draw the zero sequence network, you need to consider the neutral grounding impedance also, because the zero sequence current flows through the neutral grounding impedance. When Zn is marked in the zero sequence network, this should be marked as 3Zn. We have studied the reasons in the earlier classes. This is the zero sequence network of an alternator. So when you draw the zero sequence network of an alternator, the zero sequence impedance is there, 3 times neutral grounding impedance is there. So the current is IA0. The voltage VA0 equals minus IA0 into the total impedance Z0 plus 3Zn. Now the three sequence voltages are equal, so these three networks should be connected in parallel. Let me draw the sequence networks in parallel. Now the currents IA1 plus IA2 plus IA0 equals 0. The sum of the currents flowing towards this node equals 0. This is IA1 plus IA2 plus IA0. This is equal to 0. So both the conditions are satisfied. Now let us add one more step to this fault analysis. Suppose the fault occurs through an impedance ZF. Now we have a fault impedance of ZF. Now the potential at this point VB equals VC equals the drop across this impedance. The potential at this point with respect to ground is the voltage drop across this impedance. This is equal to IB plus IC into ZF. So this voltage VB equals VC equals IC this IB plus IC into ZF. So one condition is VB equals VC. The another condition is VB equals IB plus IC into ZF. Let us take the first condition now. VB equals VC. Let us find out the phase voltages in terms of sequence voltages. VA, VB, VC. This is equal to the transformation matrix into the transformation matrix is 1, 1, 1, 1, alpha square alpha, 1, alpha, alpha square into VA0, VA1, VA2. Here VB equals VC. This is the condition we are using first. VB equals VA0 plus alpha square VA1 plus alpha VA2. VA0 plus alpha square VA1 plus alpha VA2. This is equal to VC. VC equals VA0 plus alpha VA1 plus alpha square into VA2. It is VA0 plus alpha VA1 plus alpha square into VA2. Here this VA0 will be getting cancelled. This is alpha square VA1. This is alpha VA1. So alpha square minus alpha into VA1. This is equal to, or it is alpha square VA2. This is alpha VA2. This alpha square minus alpha into VA2. This alpha square minus alpha terms getting cancelled. So we can write VA1 equals VA2. So the positive sequence voltage is same as the negative sequence voltage. Now let us consider the second condition. VB equals IB plus IC into ZF. VB equals IB plus IC into ZF. This is our second condition. Because we split this equation into two conditions in order to get the sequence voltages, so that we can understand how the three networks are interconnected when you consider the fault impedance ZF. So VB equals VA0 plus alpha square VA1 plus alpha VA2. VA0 plus alpha square VA1 plus alpha VA2 is equal to IB plus IC into ZF. Consider the sequence current equation. This is equal to 1 by 3 into 1, 1, 1, 1 alpha, alpha square, 1 alpha square alpha. The currents are IA, IB and IC. Here IA equals 0. IB and IC exist. So here we can write IA0 equals 1 by 3 into 1 into 0 plus 1 into IB plus 1 into IC. So it is IB plus IC. Or IB plus IC equals 3 into IA0. So it is 3 IA0 into ZF. Now, in our case, VA1 equals VA2. So we can write this as VA0 plus alpha square plus alpha into VA1 equals, because these two voltages are equal, VA1 equals VA2. 3 IA0 into ZF. What is alpha square plus alpha? You may remember 1 plus alpha square equals 0. So alpha square plus alpha equals minus 1. So VA0 plus minus 1 into VA1 minus VA1 equals 3 IA0 ZF. 3 IA0 ZF. Or VA1 equals VA0 minus 3 IA0 ZF. So this is our another condition. So the sum of the sequence currents equals 0. This is one condition for the sequence current. The positive sequence voltage and the negative sequence voltage both are same. And VA1 equals VA0 minus 3 IA0 ZF. These are the three conditions we are using to draw the sequence network including the fault impedance. As VA1 equals VA2, the positive sequence network and the negative sequence network should be connected in parallel. You look at the second condition. VA1 equals the positive sequence voltage equals the negative sequence voltage minus a drop. What is the drop here? 3 into IA0 into ZF. So the drop should be marked as, this is 3 ZF. Here the current is IA0. So this drop will be 3 IA0 ZF. Now we look at the current equation. The sum of the sequence currents equals 0. What are the currents coming towards this junction? IA1 plus IA2 plus IA0 equals 0, because there is no current leaving at the junction. We are applying the KCL, Kirchhoff's currents law. The sum of the currents coming towards the junction equals the sum of the currents leaving the junction. So the currents coming to this junction is IA1 plus IA2 plus IA0, that is equal to 0. So this condition is satisfied. Now positive sequence voltage and the negative sequence voltage are equal. So they are in parallel. And the last condition is positive sequence voltage equals this zero sequence voltage, this is our zero sequence voltage, minus a drop here. The drop is 3 ZF into IF0. So using this network we can find out the three sequence currents, IA0, IA1 and IA2. From the sequence currents we can convert or we can find out the phase currents. From these sequence voltages we can easily find out phase voltages. So this is the complete sequence network for a double line to ground fault, including the fault impedance.